All right, week one, we are going to be taking a look at charges and charge interaction. This week is a little bit lighter than every other week, as we're really basically understanding the fundamentals of charge, and then we're going to apply that in all kinds of fun ways throughout the next several weeks. So if I did units, I would have a unit of electrostatics, which would essentially be now through week 5. Today, again, this week, we're doing the charges and interactions, how things become charged. Then we'll get into electric forces, electric fields, electric potential, and electric flux. So if you've taken any sort of chemistry or any science, really, you know what an atom is, and hopefully you know what makes up an atom, which is your protons, electrons, and neutrons. Okay. We know that the protons and electrons live here in the center in the nucleus. They make up the majority of the mass of the particles, and our electrons are orbiting around in these electron shells, these energy levels around the nucleus. We're not really too concerned about neutrons. In this case, we're more looking at the actual charges and the net charge. And so that net charge is going to be dependent on the number of protons and electrons. And because the protons make up the bulk of this, it's only going to be the electrons that are actually transferred from one substance to another. Okay, we cannot transfer protons. Well, we can't in our labs. For instance, if you take a helium atom and you remove a proton, it now only has one proton, which now it means it's actually hydrogen. So the number of protons actually defines the element itself. So protons are not lost or gained, it's only electrons. So charge is a fundamental quality similar to mass. Okay, we know the masses of things, but what the mass actually means is a little abstract. Okay, we know it's the amount of stuff that makes up a particle, but what does that mean? Okay, so what does it mean to be positive or to be negative? And essentially those are coined terms to know that they're opposite. Okay, we could have said these are ups and these are downs, just knowing that they're opposites of each other. Okay, the fundamental charge is measured in coulombs. We're going to have a lot of units named after scientists, and anytime a unit is named after a scientist, it must be capitalized. So capital C for coulombs. Charge is a lowercase q, okay? Sometimes it can be also as an uppercase q, similar to mass. When we look at forces, like planetary mechanics, we usually use a small m and a large M for an object and a planet. We're going to do kind of the same thing next week and the week after for bigger versus smaller charges, source charges versus point charges, but either Q's work, okay? And it is a scalar. My exponents did not work here, 10 to the power of 18. So 1 coulomb is a very large charge, okay? A lightning bolt has 10 to 20 coulombs. All right, so we're going to be dealing with the micro and nano coulombs a lot of the time because coulomb is a huge amount of charge. All right, to have 1 coulomb of charge, you would have 6.25 times 10 to the 18 extra electrons. And then an electron itself has 1.6 times 10 to the negative 19 coulombs. So that's 10 to the negative 19. Same thing with the proton, okay? Although they have wildly different masses, their charge are the same. They're equal and opposite. So 1 electron and 1 proton cancel each other out to have a net charge of 0, all right? Electrostatic forces, we're going to be using a lot of this for calculating that next week, for week 2. And this other law of charges here, everybody kind of knows this from playing with magnets. Like charges, they repel, and unlike or opposites attract, right? So when you have a negative electron and a positive proton, those are going to attract together, as opposed to a negative and a negative, they're actually going to repel. And this just goes to the size. These are good reference points. I'm going to bring this up again probably next week. You'll need to know the mass of a proton or the mass of an electron sometimes. And again, I apologize for all my exponents. This should be 10 to the negative 27 and 10 to the negative 31. If you need a number like this, a constant, I would provide that on at the beginning of your quizzes. All right. You will be making an equation sheet throughout the semester, and so little information like this is going to be very important to have a reference between how many coulombs are in an electron or how many electrons are in a coulomb, okay, or the masses of these. And so if you want to start already making note of these, that's a great idea. I'll explain more for this equation sheet and reference sheet as we go. So here are two practice calculations. These are actually very similar. Okay, so a common static electricity involves charges ranging from nanocoulombs to microcoulombs. So how many electrons are needed to form a charge of -2 nanocoulombs versus we have here 0.5 microcoulombs. If you do not remember your metric prefixes, please make sure you're writing those down. I will have some more details with those later, but we will have to convert all of those to base units. So nano is 10 to the negative 9 regular coulombs, and micro is 10 to the negative 6. Now I took this right from your textbook here. So we have 2 coulombs, and then we're changing, we're dividing by the charge per coulomb in order to get how many electrons that we would need to get that charge. Okay, notice that our nano is 10 to the negative 9 regular coulombs. Our micro is 10 to the negative 6 regular coulombs. We're doing the same thing, and then we can just compare those. Okay. So essentially this is just unit analysis. I've got my coulombs divided by my coulombs, and I know that I would divide in this case. You do have 2 or 3 practice questions like this, maybe 3 or 4 in your homework for this week. So how do these become charged? Atoms become charged when they become more positive or more negative, and it is the electrons that are moving. Okay, so if you're positive, that means you have lost some electrons. You've lost that negativity. Okay, if you're negative, then you've gained some negative electrons. All right, similar to if you've ever done ionic bonding, it's the exact same thing. Okay, our sodium here is going to lose an electron to become positive. Our chlorine's going to gain that electron and become negative, and then that positive and negative attract each other, and that's how you get that chemical bond. Don't worry, we're not doing compounds in here. It's just a reference point for those of you who have done this. If you don't know what I'm talking about right now, it's okay. Just like mass, we have a conservation of charge. You cannot create and you cannot destroy charges. They have to go somewhere. Often they get grounded. And what grounding is exactly what it sounds like. You actually put things back into, or put charges back into the ground. All right, so if you have something like a lightning rod on a building, that is literally attached back down to the ground. So to be grounded is we're bringing these excess electrons back to kind of cancel everything else out. Okay. So we do have insulators and conductors, just like in heat. So insulators do not let electrons move around freely. So something like plastic, any wire that you use on a daily basis has a plastic coating around it, or rubber coating, depending on the quality of the wire. Okay, that is protecting, it is insulating the copper or whichever metal is inside that, so we don't get shocked every time we touch a wire. So a little public safety, if you have, extension cords that are kind of frayed at the end, they tend to get frayed the most. Wrapping some electrical tape around it. Electrical tape is an insulator, so you can keep using them, but obviously it's a safety problem. So there are 3 ways we can charge an object, okay? And again, we are talking electrostatics, so we're talking non-moving charges. So we're going to transfer them from one thing to the other. However, they are not flowing like a current, okay? That will be our second unit when we get into current and circuits. Okay, so, and just to reiterate that the only thing moving here is our electrons. So we've got 3 ways: friction, conduction, and induction. Okay, the first 2 are pretty obvious. Friction, we literally rub two things together to create that friction, and they have to be two different materials, and the electrons are being stripped from one and going to the other. All right, so this is where if you've ever had clothes in a dryer, if you have like a nice fleece sweater and some cotton socks, fleece and cotton are a little bit different, and so when they rub together, you're actually, one of them is taking the electrons from the other, which means one becomes positive and one becomes negative, and then they attract each other again. All right, and so that's why I think clothes get stuck together. Same thing happens with lightning. Okay, you actually have clouds that are moving between each other or within each other, causing that transfer of electrons, and then you build up this excess charge. Okay, this is a super fun word to say. It's called the triboelectric series. And what that is it's pretty much like on a periodic table, you have electron affinity. So we kind of know who's going to give up an electron and who's going to take an electron in chemistry. Same thing here with electrostatics. Okay, so human body, we make great conductors. All right, and there's all kinds of things. Maybe that's not the best. So let's take a look at wool. Okay, wool in the human body. If you're wearing a wool sweater, okay, I know it's Phoenix, but maybe you're up north somewhere or in the winter. You wear a wool sweater, you take that off. The rubbing of the wool on the human body is actually transferring electrons. And what this means is whoever is higher on this list is most likely to be positive. So the human body would actually become positive and the wool would be negative. So the wool is taking electrons from your skin, okay, or body. So another one, if we take a look at, where is it? Well, let's take a look at aluminum here. Okay, if I have aluminum and then I rub it with the wool, okay, in this case, the wool is actually higher on the list. So now the wool is actually going to become positive and the aluminum is going to take those electrons from the wool. Okay, and so that's how we kind of know what's happening here. And anytime you have charging by friction, you end up with one object charged and the other object with the opposite charge. So you end up with one positive and one negative. So here is an example. I took this from your book. I take a lot of the diagrams from your online book through OpenStax. So if we have amber and cloth, okay, they're electrically neutral. All right, 2 positive, 2 negative for our amber, 3 and 3 for our cloth. Once they rub together, all right, what's happening here is that our amber is actually taking electrons from the cloth. So if we look at our net up here, we now have a negative amber and a positive cloth. Notice though that your positives never changed. It's your negatives, okay? Your protons cannot move. I mean, they wiggle and vibrate and all that kind of fun stuff, but they don't transfer, all right? So it's now our amber has 2 more electrons, therefore it has a net charge of negative, and which leaves our cloth a net charge of positive. And this is a different triboelectric series, but they all do the same thing. So if I find amber here, okay, and cloth, we're going to go ahead and call that cotton. Okay, we're going to assume it's a cotton cloth. That's why I know my cloth is going to end up being positive, and I know my amber is going to be negative, right? Because my amber is lower on that list. Now, if I took, again, a different situation, cotton, and rubbed it on glass, okay, now my glass is going to be positive and my cotton would end up being negative. So it's kind of that hierarchy of what is happening. Okay, notice things like cat fur or rabbit fur. A lot of these things, if you do have pets or a dog with kind of fluffier hair, if you've ever pet them or combed them, essentially your plastic comb or your plastic, depending if it's a metallic brush or a plastic brush, you're actually stripping electrons from the fur, which is why it gets very staticky. Okay, and cold, dry air is actually when electrons move the most. or it's the easiest. That's why in the winter, when it's a little bit colder, but also very dry, that's when we get a lot of static electricity. Okay, same thing with your hair. If your hair gets staticky, it's because the comb or brush is actually stripping electrons. So there you go. All right, so moral of this story is charging by friction, you always leave one object positive and one object negative. So you have two objects that are neutral, they get rubbed together, and then we get one positive and one negative. Same thing if you've ever rubbed a balloon on your hair, you're doing the same thing. The rubber balloon is taking electrons from your hair. Your hair stands up because now all of your little strands of hair are positive, okay? And as we said, positives don't want to be by positives, so that's why your hair stands up. It's actually trying to get away from all the other strands of hair on your head. Conduction, we have conduction is by touching, okay? So in this case, you actually have to start with a charged object, and then you physically have to touch that, and so you're going to get a transfer of charges one to the other. Now, this does not leave this one completely neutral. You would have essentially when they're together, they go to equilibrium, so these charges are equally spread out. So you will end up with two charged objects still with the same charge, just the original will be a little less. And in this case, your electrons are moving from the rod to the sphere. But the same thing could happen that if you have a positively charged rod and you touch it to a neutral sphere, okay, the negatives are actually going to leave the sphere to try to neutralize that rod, which means then we would have an overall positive charge in that case. Okay, so whatever you're starting with, that's what both objects end up with. So if you start with a negative rod, both end up negative. If you start with a positive rod, both end up as positive. Okay, induction is different. Okay, induction is where we are temporarily polarizing an object. Okay, and what we mean by that is we start neutral, then we take this negative object and we're approaching it. We are not touching it. As soon as we touch it, it goes back to conduction. We are approaching it, and notice here there's no transfer. Okay, those electrons are essentially rearranging themselves. They're kind of moving away from the negative rod, which makes it polar. So you have a positive side and a negative side. And then if you take that away, if you remove that, it goes back to neutral again. Okay, so here are a couple examples of what it would look like. Obviously, this is exaggerated because they're diagrams, but it's to get a good idea. Okay, so this is positive. It's attracting the electrons, so these atoms are rearranging themselves to have a more positive side and a more negative side. So we've got our negative over here and our positive over here, so this is polarized. Again, as soon as you remove that, this would go back to neutral again. Okay, now the difference is if we tried to charge it. Okay, so let's say I put a second object here. What would happen is that this positively charged and this positive edge is actually going to attract some of these electrons. And if these are touching, these electrons are actually going to move here, leaving this object. And then if I separated them out, I would end up with a negative sphere and a positive sphere. Okay, this has a really good description in your text on this one, but essentially it's going a step further. So you start with induction, you're inducing this polarization. Then once you put them together, so you have conduction, they're moving to have a negative and a positive as one, but as soon as you separate those again, then they're going to be charged. Okay, and here are just a couple other diagrams there. Okay, so you've got a few of these practice in your CFU, your check for understanding, which means you'll mostly likely see one on a quiz too. So in this case, you have two balloons are hung from a ceiling by threads. If balloon A is positively charged and balloon A and B repel, what does the other have to be? Well, this has to be positive as well, okay? Because the only way you can repel something is that if you have two like charges. So the only option is for it to be positive. Now, that is for repelling, okay? Electrostatic forces and magnetic forces are the only two forces that we currently know of that have the ability to repel without actually touching. Yes, we could push something away, but that is a physical force. This is a non-contact force, all right? Now, the tricky part is charged objects can actually attract neutral objects, right? Because we just said, well, we can induce this charge, all right? Because right now we're looking like we have a positive side, so this negative is actually attracting that. So even though this isn't charged itself, it's technically electrically neutral, but we're still attracting it. For instance, right here, if we have two balloons and A is positively charged, okay? We know B cannot be positive. There's no way, otherwise they would repel. So we can say that B is negative, but B might not be negative. B could also be neutral, right? Because if this is positive here, we could just be inducing a negative side to it where it is polarized, but the whole thing is actually neutral. So in this case, we don't actually know whether it's negative or neutral, but we know it's one or the other. Now, in order to figure out if it's one or the other, okay, we're going back to the same situation here where A is positive. So without looking at what B is doing over here on the second situation, we know that B has to be either negative or it could be neutral, right? But now if we take the same balloon and we see that it is attracting neutral paper bits, okay, neutral cannot attract neutral objects. So if my paper bits are neutral, but it's being attracted to my balloon, then we know that this balloon is in fact negative, right? So it was attracted to A because it is polarized, and then, or it could have been polarized, but the fact that it is able to attract these paper bits means it's not just polarized, it has to actually be charged, therefore B would be negative. All right, I'm gonna let you try to figure this one out on your own and check your answer on the next slide when you're ready. And then our little summary here, just to wrap things up. So we have charges, they're positives and negatives coming from the protons and electrons, and they are measured in coulombs. All right, again, 1 electron is equivalent to 1.6 times 10 to the negative 19 coulombs. Please keep that for your reference. You will need that number throughout the semester. We also know that 1 coulomb is equivalent to 6.25 times 10 to the 18 electrons. Okay, and that's a negative coulomb. If it was positive, then it'd be protons. All right, that number we're not going to use as much. You're going to use it in your homework this week, but not a whole lot throughout the rest of the semester. It's more of the charge of an electron and a proton. Okay, we also know that like charges attract and repel. Electrons are the ones that are transferred. When we have an excess or more electrons, we're negative. If we lost electrons, then we're positive. And we looked at the 3 ways objects can be charged by friction, conduction, and induction.